Go back here.
Okay, thank you everybody. We are going to start our celebration of 100th NIA CFD Seminar. As always, thank you very much for coming. Today we are all in a very celebratory mood, and the program, first of all, I'll tell you the program of today. So I'll say a few words. I'll say a few more words. I already started. Then I'll ask our NIA President, Doug Stanley, to say some few more words. And then we have our actually essential, the most important part of today, the actual NIA CFD seminar, and Hiro is going to present at this seminar. After this, we will have some ceremony of candle blowing, which will celebrate our occasion. And after this, some food will magically appear in the back room. So we will have like maybe 5-10 minutes so that you can go there to take some food, come back, and during the lunchtime, I will be the lunchtime entertainer here. And after this, because from everybody, typically after a birthday party, people have to leave with some presents. So we will have a raffle, so some people will leave with some presents. But that's going to be the program for today, and after this, we will all have to go back to work. So now I start my few words that I want to say before this seminar. First of all, I want to thank the people who, NIA people who make all these 100 events possible. I want very much thank Rita, who is our IT backbone, so we always lean on her, and she's always here to make sure that our camera working, that our technical glitch is solved, and that our NIA CFD seminar presentations on website, and most of them acceptable. So we want to thank Mary Catherine Bundy, because she's the one who is keeping us on schedule, even if we are 5 minutes late. So she is sending all this announcement, making sure that people know what's going on, and she is basically the one who is responsible that we are all happy and healthy and in a good mood, so that we all can function and live kind of happy life. I want to thank all the people who are coming to our NIA CFD seminars, just because this is an audience, and we are presenting it for people who want to hear it and who want to use it. But most of all, I want to thank people in the blue hats in this room, because those are people who actually presented at NIA CFD seminars, those people who make it happen, and those people who made us to this number of 100. So thank you very much, everybody. And with this, I'll ask Doug Stanley to... Oh, we want to thank also NIA administration for financial support, because I think that the great refreshments is the second most important reason why people come to this NIA seminar. And I believe that the first most important reason is the quality of NIA CFD seminars, and I hope that I got the order right.
I'm Doug Stanley, President and Executive Director of the National Institute of Aerospace. Some of you who follow us online may not know exactly who we are, but we're about a $34 million a year research, outreach, and graduate education institute. We're a consortium of 9 universities here in Hampton, Virginia. And when I came on as Vice President of Research 6 years ago, and then I came on as President 9 months later, the board really wanted us to organize various centers. And so our very first center we organized was the Center for High Performance Aerospace Computations that Boris pulled together. And it's really been our largest and most active research center and activity here, thanks to Boris and his leadership. The seminars actually started before that, back in 2011. So over almost 7 years now, this will be our 100th seminar. And so thank you, as Boris mentioned, all you who presented. And we're going to be very pleased, and Boris will introduce Hiro in a minute, his partner in crime here at NIA. And Hiro has actually given more seminars than anybody else. I think it's like his 13th or something like that. 12. He's very creative, as you know, from his capabilities. But first of all, we just want to thank Boris, because we only have had 3 fellows in the history of NIA, and he's one of them. We give him the status of fellow based on his extraordinary research contributions. He's been at NIA all 15 of our years. Before that, he was at iCase here and providing exceptional leadership there with his work on adjoint methods for optimization and unstructured grid methods and such. And Boris, he was, you may know, was co-authored with Eric Nielsen, the best paper at NASA Langley Research Center a few years back, and was also named the Hampton Roads Section AIAA Engineer of the Year. And so Boris has had a lot of honors, and so please join me in thanking him for his leadership. So the HYPACK Center has been around now for several years, and lots of folks have won awards. Hiro has been kind of Boris's partner in crime over the years, and Boris will introduce him in a minute, but his extraordinary work on hyperbolic solvers and agglomeration methods for very fast CFD are well known. In fact, he was just honored with the best CFD paper in AIAA this past year, and that was recognized for that at the SciTech conference that I was at. So we thank him for his leadership here for HYPACK as well, and all of our researchers. We typically have 8 or 10 NIA researchers involved, about $2 to $2.5 million a year, about 8 to 10 universities in any given year, and probably 5 or 10 visitors over the course of a year, often international visitors that come here, all as a part of this extraordinary effort of HYPACK. So I just want to thank that, and I also want to thank the research that happens here has been made possible from generous grants and research grants from NASA Langley and NASA in general, and folks like Mujib Malik and Bill Klebb and Susan Gorton, Joe Morrison, Peter Cohen, Steve Rizzi. We thank them for all their financial support over the years, and all of our technical collaborators with CFD, many of them from NASA are here in this room. We thank you for coming out and making this possible over the years, and our viewers at home. We get hundreds of views of these seminars, and if you don't know it, and these are all online and saved in our media site website, and so you can view all these in your spare time if you want to go back and do. Everyone likes binge watching. You know, if you want to do binge watching of CFD seminars, you can do that. They're all there on the website. So, and if you could just pan around, read us, because some of you who are here, you don't really get to see what happens here at NIA. You just see the speaker. But thanks to Mary Catherine, we have a wonderful party what's happening here with balloons and hats and such, and a cake we're going to cut after the seminar. So I'm sorry that those of you following us online won't be able to be here, but if you're ever in the neighborhood, please stop by NIA and visit us. And thank you to Steve for helping put this on. I saw we're reaching about our 96, 97 seminar. I went to Boris and I said, I want to do something special for 100. And so MC and Boris helped organize this. And so we do have lunch for you, so stick around for that. And as Boris said, we'll be our lunchtime entertainment, kind of give you a little bit of history of HYPACK and seminars over the years. So with that, Boris, come up and introduce our speaker. Thanks for you guys.
Okay, now to NIA CFD Seminar. So today our presenter is Hiro Nishikawa. I will not list all his awards because most of them I will list in my presentation during the lunch. But today about this topic. So as practical CFD researchers, we always complain about grids. So the grids we are computing on are never satisfied. They're not smooth enough, they're not square enough, they're not good enough. So what today's presentation is probably going to tell us is that we probably place our blame not in on the right subject. And maybe something else is not right, not necessarily the grid. And actually the fact that we can have bad grids with very irregular grids with zero negative volumes, that maybe opens for us some new opportunities that we never had before. And this kind of groundbreaking contribution that Hiro is going to present is maybe a way, opens a way how to use this irregular bad grid for our advantage. And as Doug mentioned before, this paper was presented at Aviation 2017, and this paper was awarded the best AAA CFD paper of 2017. And with this, Hiro, please take the podium.
Thank you. So you already got a chance to read this title, zero and negative volumes. In CFD, it means invalid or impossible. The CFD code will not take such reads. It says zero negative volume, just go back and fix it. But in this talk, it is going to be claimed that these zero negative volume elements are useful, and they bring advantages for future CFD simulations. So this is going to be a very, very strange story, like an episode from the classic TV series, The Twilight Zone. This is a CFD Twilight Zone episode, the forbidden capability. So it is often said that most great inventions begin as a crazy idea. But the crazy ideas should be handled carefully. If you are to get excited about it and drawn into the craziness, you would be trapped and never be able to come back to the real world. Dr. Nishikawa, a CFD researcher, he encounters an unusual and amazing capability of CFD. But it is just too crazy, nobody takes it seriously. So he struggles to prove that it is real and useful in an attempt to escape from the Twilight Zone. Back in 1997, he was beginning PhD student at the University of Michigan, working with Professor Rowe. Professor Phil Rowe came back a year earlier, in 96, came back from IPS with a brilliant idea for mesh adaptation. You look at this triangular grid, the solution values are stored at these nodes, and you find a region by integrating the equation you want to solve over each element. And this creates an overdetermined problem, and he's proposed to minimize this region, the measure of the error, with respect to not only the solution values at the node, but also the nodal coordinates, x and y. So through the minimization, the solution is updated and the grid points are updated. And he found an amazing result for hyperbolic equation, that this method creates characteristic mesh on which exact solution can be found. And Hiro's task was to try this out for elliptic probe, the Cauchy-Riemann system. And here is an example. This is an implicit version of the Riemann cavity probe. It's a source and a sink, so the flow is going that way. This is streamline. He tried this method, starting from uniform triangular mesh. The expectation is that the grid point will move towards the singularity after two corners. And one day he ran this method and see the residual converge to machine zero without any sign of difficulty. And when he plotted this grid, he was surprised, because the method converged to this mesh, and these points move too much, and this one goes out of the dome. But solution is found when plotted on this mesh. It looks reasonably good. It looks more like the exact solution. So this was the beginning of this strange grid method. He showed these results to people, but nobody took it seriously. They say, you must fix the grid. This grid is wrong. There must be a bug in your code. Your code is wrong. But no matter how many times he tried, he can get a solution or entangle the mesh. And he started to look for explanation. And one explanation he found is from the geometrical theory of mathematical physics. The solution of a pair of PDEs in two dimensions, space dimension, is actually a surface in a four-dimensional space. So here's the surface in a four-dimensional space, x, y, and u and v. These are solution variables. So all variables are independent. The solution is an object, geometrical object. And numerical approximation, the triangulation, what it tries to do is to approximate this solution surface by triangulation, by adjusting the location of these nodes in this four-dimensional space. Typically in CFD, we only seek solution on a fixed grid. But this method seeks try to find the best approximation to this surface in a four-dimensional space with through this grid. And he was able to show mathematically that the residual is actually a measure of error in aligning a triangle tangent to the surface. So in that sense, it doesn't matter whether a triangle is invalid or not. As long as it is tangent to the surface, it is accurate. So this explanation satisfied him, but nobody else. But the bottom line is that he was able to graduate in 2001. And in his two PhD thesis, there are a couple of more interesting results. Let me show you some of them. So he tried this minimalization scheme on a fixed grid. This grid looks good. This is called good grid, right? But this scheme is so bad. It is this is a typical odd-even decoupling or checkerboard error mode. So the pressure distribution is so simple. But once he started to move the grid and update the solution at the same time, this is what he found. Now the grid has checkerboard perturbation, and now the solution is perfectly smooth. And this grid is typically called bad grid because the grid lines are not orthogonal. So the implication here is that bad grid can be a good grid for bad scheme. And his advisor was very intrigued by this. Also because you can do a tangled mesh, and he tried to solve a linear relation with discontinuous solution. And the method actually converged to a zero volume, perfectly captured discrete grid. This is a linear relation, but he later extended it to nonlinear shock for the oil and published a journal paper. Another one is this. This is a supersonic flow-through adapt, and based on the linearized aerodynamics. So this is a linear hyperbolic system. On a fixed grid, your solution is typically diffused. So these thin lines are the solution contours. But once you move the grid adapts itself to find the characteristic paths and then find the exact solution for a given boundary node distribution. And what intrigued his advisor was that this result was obtained by removing nodes. Sometimes the nodes to the edges try to represent the same characteristic. He had to remove some nodes. So 18 nodes were removed to capture shock there. And probably that was the only result, the first result for capturing shock without adding points. The last one is the third order accuracy. He observed the third order accuracy on the linear grid already in 2001. He recently implemented a third order scheme into FAN3D. And this method achieves third order without high order mesh. And still some people don't believe it. But he knew since 2001 you can actually get slope through in error convergence. And later he extended to a multi-grid third order solution for shipping. But after graduation, he started to work on some other stuff, and this interesting topic was kind of forgotten. 13 years later, he started to work at NIA. In 2014, for the first time, he wrote 2D Navier-Stokes solver. And he was so excited. He tried this to solve for various kinds of problems. And this is a viscous flow over pump, which is this little pump here. But he wasn't very satisfied with this perturbed grid. He wanted worse grid. And he perturbed it, but without looking at the grid, ran the solver. It converged in 10 iterations to machine zero. No sign of difficulty or any problem. But when he plotted this grid, it looks crazy. But solution was obtained. And another surprising fact is he plotted the pressure distribution over this little pump and compared these two cases. And they look in good agreement. So this grid can be used for CFD simulations. So his memory came back, and CFD on the tangled grid. He tried to talk to other researchers, and the truth is he's not alone. Many other CFD researchers have a similar experience, but no formal publications were found. And he begins to understand why. Because there's a big question that nobody was able to answer. And big question it is. So what? Who wants to use such bad degree? Okay, you can get the solution, but why do I want to use such a bad degree? And he continued to think about this, and then 2 years later, in 2016, finally, he came up with a good question. Okay, how is it useful? So CFD on band grading is robustness, yes, but it is almost always possible to fix the grid. And there are people who work on the grid generation. And unless the scheme is proved to work with zero negative volume elements, and the use of them brings advantages, it generates no interest. And it doesn't lead to any publication. So, with this question in mind, he began to make moves. At the time, he was working on this edge-based discretization. This is a popular discretization used in fancy Cradle software, SC here, Hardware. You want to solve this conservation law with a conservative approximation. So this is the sum of the fluxes over these edge midpoints, over this zero control point. And the numerical flux is computed typically by upwind flux or central plus anticipation. And solution and flux are linearly extrapolated left and right space at that edge midpoint. This edge-based formula is a very special scheme. But second, this achieves second order accuracy only on simplex triangular and heterogeneous elements. For other elements, you need some regularity to achieve second order accuracy. And recently, it was found that this achieves third order accuracy with quadratic reasoning on simplex grids, only on triangle and heterogeneous. And there is a theory published Hiro and E in JCB reasoning. In this work, he considered only two schemes. So conventional scheme, advection diffusion, second order accuracy on triangles, and hyperbolic scheme. Basically, this means third order for advection. So this is both are second order scheme, but this is a special feature. It has it achieves third order for advection. And only the model equation is considered in this paper, and Euler and Navier-Stokes will come later in the future. Here's the assumption. Assumption on grid is that it can be mapped to a grid of all positive schemes. So actually this grid, it has a negative volume elements, it's completely invalid. But this was created by adding quadrilateral to these nodes from this grid. So the connectivity is exactly the same. And all grids that will be shown are generated from some kind of refinement by quadrilateral. So he looked at this edge-based scheme on this bad mesh, but it turns out that there is no modification necessary, and you should. So the bottom line is all computed such that element has a positive volume when its nodes are ordered, counter-clockwise, like this. So you don't look at the grid, just based on the ordering, you compute directed area vector and dual volume for each node. It's a sum of these triangular pieces. So just assume that nodes are ordered counter-clockwise. So depending on the ordering, the volume can be negative, but keep that negative volume because you need this for consistency. So do not modify existing code. For example, the directed area vector for this node will be these two pieces. If you move this node J to 1, now the triangle vanished. But these directed area vector still have a finite length, still there. And if you move this node further to the right, you get an inverted triangular element. Now the directed area vector flips. But don't look at this. Just use it as it is. Because we need this condition, the normal vector, the sum up to 0 around each node for consistency. If you flip this, you will violate this, and there will be a lot of problems. So do not even check. It is good not to look at the grid. And the dual volume is actually independent of the location of node J's here. The dual volume is the volume around this node. But no matter where this node is, the volume is actually exactly the same. If you move this node J to 1, yeah, these two elements vanish, just zero volume. But the dual volume is exactly the same. If you move it to the further right, still you have some negative volume, but you have more positive volume, and they cancel. And you can actually look at the mathematical formula. This nodal coordinate J cancel out. So don't change anything. The zero negative volume as they are, so that we maintain a consistency condition. Because the volume, the sum of the dual volume, must add up to the entire domain. If you change anything, you will violate. The source term integration will not be correct. When negative volume, dual volume happens, if you take this linear direction equation, and here's the H-based discretization. If the dual volume is positive, if you expand this Taylor series, the leading term is the equation you are trying to solve. If there's a negative volume, what you find is a negative sign appears in front of the equation you're trying to solve. And this might be a problem for unsteady problem, but it's the same thing. If you look at the unsteady equation and the region, this volume is negative. And this will produce negative of the equation you're trying to solve. So all the equations have just a negative sign. So you are solving the same right equation. But in this paper, we didn't consider unsteady problems. These were gradients. You have to compute the gradient at the end. But this school method doesn't look at elements. It's just a point. No problem. But when you have a zero length edge, and if you're using inverse distance weighting, you have to be careful. And he found the H-based scheme, if you construct, this nodes 3 prime to 3 and J prime to J, 6 prime to 6, just move them on top of neighbor points, so creating zero volume elements inside. In this case, the H-based residual becomes the Rankine U volume condition. So if there is a shock along this line and a solution, here there are actually 2 points here. If they satisfy Rankine U volume, you have a zero residual. And all these methods, for the test case, he employed Newton's method. And no pseudo time, it's just a Newton's method, and conversion 10 iterations, maximum 17 for all test problems. And here's the accuracy verification. This is a regular grid, no negative anything. This grid, this one grid line moved to the next grid line. So there are zero volumes along this line. And this volume, like I showed before, the nodes are moved outside this dual volume. And this one is a completely irregular triangular grid. It has 8 negative volume elements, but he generated a final mesh independently and checked their accuracy. And he obtained the accuracy as he expected. A hyperbolic scheme, third order accuracy, and a conventional second order. And it's interesting, the lowest error, this green one, is obtained on this. This should be a good one, right? And if you plot the grid on technical, this one is weird, a little bit irregularity here. But it doesn't matter, because nodal solutions are accurate. They almost have the same accuracy here, right? So this is just outcome of the plot. And now he was ready to answer this question. How can they be useful? There are 5 examples. First one is this. Because like I said, H-based scheme achieves second order, third order only on triangles. If you are given this unstructured, irregular quadrilateral grids, you have to subdivide into triangles to achieve third order. But if you do it randomly, just split each quad into 2 triangles. If you do it randomly, you generate a lot of negative volume elements. This example has 113 negative elements. But, no problem. Don't look at the grid, don't check the volume. Because it worked, hyperbolic scheme, the third order accuracy, and on class, as expected, it's not even second order, it's only first order accuracy. And in this case, the pure volumes are all positive. And if you look at this one really capturing this Burroughs equation, there is a shock running, it should be straight. But on this unstructured grid, you get some distortion. And he created the perfectly shock aligned mesh with zero volume elements, and the method converts to machine zero rapidly. And these elements you see here, you don't see them because it's zero volume. But it represents perfectly the discontinuous solution. Another interesting example is the singularity. This is a potential flow problem, the Laplace equation for string function. So here's a kind of flat plate. The flow is going around this flat plate. So I'm indicated here. And this tip of the flat plate is a singular point. The solution is actually continuous everywhere, but the gradients have multi-value at this point. And this is a very difficult problem. And theoretically, it was proved in 1967 by Rasmussen that the best you can get is only first order accurate. So he tried to tackle this problem with zero volume elements. The idea is to generate a first grid practice around flat plate and then move these nodes onto the flat plate. So these 6 nodes go into the same location at the tip of the flat plate here. And so we have 2 nodes here, 6 nodes in the same place, trying to resolve this singularity, the multi-value at the same point. And he can have lots of points to resolve this. So he compared 3 different grids, a regular mesh and a similar mesh, but with only 1 point at here. And this one has a lot of points. And then you can see the contours much smoother here. And also, he achieved a second order accuracy, which was not impossible on other grids. This is only first order accuracy. And this has an application for the training edge of airplane or wind. You can place a lot of points. Another one is a hanging node. This type of grids are used in some other schemes, but edge-based scheme doesn't directly apply to this this type of mesh. You have to modify your algorithm. But with zero volume elements, you can make it non-hanging. So you introduce these triangular elements here, and then push these nodes back onto the midpoint of the edge. So this is the result. And this one has 2 nodes from these 2 sides. So this looks like a hanging node grid, but it's not. This is a mixed grid, quadrilaterals, and zero volume triangles. So the edge-based scheme works. It just takes this grid and then it works. But to achieve third order and second order, you have to triangulate. And you can do it, in this case, easily. Each quad subdivided into 2 triangles. And he observed a second order accuracy by computational scheme, and third order accuracy by hyperbolic scheme. This implies that we can, in 3 dimensions, we can subdivide prismatic elements locally. It can be an efficient adaptive method for practical applications. The final example is the overset grid. The overset grid, there is a little, this smaller piece of grid, and on top of it, it has a larger part of grid. And this is their overset. And this is a very practical technology used for moving body problem. But the problem is that these 2 grids are disjoint. Somehow you need to transfer information, like interpolation. And you can probably do a conservative interpolation, but the discrete conservation is really hard to achieve because this is simply disjoint. But with the negative volume elements, you can connect these 2 into a single grid. And once this is done, it simplifies coding. No interpolation, no two grids, just one grid. And this grid conservation is just trivially satisfied. This is one grid. And let me show you how this is done. So on this grid, just for the visualization, it is given some Z coordinate. So it's up and down. And in between, this is a completely flipped negative volume element. But this is one grid. And edge-based scheme works on this grid. So he confirmed second-order accuracy and third-order accuracy by having this scheme. And he plotted the solution onto these two grids separated, and they look perfectly fine. They match. So Hiro demonstrated the usefulness of zero negative volume elements and successfully published a conference paper. But there are a lot to do still. There are more details still in unsteady and unsteady problems and Euler analysis of difference. So his conference paper, well, in future, could turn out to be recognized as a landmark paper, or could be forgotten and buried in the shadow of the Twilight Zone. Questions on how to get out of that zone?
Otherwise, we're all going to be stuck there. No, serious questions. It's a serious presentation. We're in celebratory mode, but we want to push science.
Yeah.
Have you started any of the unsteady simulation capability? I have some concerns with regard to unsteady boiler in that it's Rankine-Unigonia equations are not enough.
Yeah.
Because the discontinuity breaks up into at least two discontinuities in expansion. And so somehow the physics of how that discontinuity moves have to be captured. And I don't want you to think I'm saying that you can't do it with that method. I can't envision how you do it yet. And I'm wondering if you had a chance to think about that.
First of all, unsteady is probably easy. It's a series of steady problems over each physical time step. I haven't tried, but I will. But I don't see a difficulty there. But the shock capturing, that's you need a means to detect the shock properly, and then align the grid, and then you can get the solution.
So you mentioned that your algorithm, moving the grid is part and parcel of what you did, at least for your PhD.
Mm-hmm.
So I would assume you need to do something like that.
Yeah.
How are those? Can you talk a little bit about how the mesh points work? Well, what are the equations that one uses? It's the minimization of the residual.
Yes, minimizing the residual. Because triangular grids, you have twice as many elements than the nodes. So if you define the residual over elements, you have a lot of there is freedom to play with, and you add this x1 coordinate. And what is interesting that for hyperbolic problem, you can actually show that the triangle tries to collapse to form a characteristic direction. You can show this. For elliptic, to kind of move towards the high gradient region. So there are mechanisms there, but it's hard. The tough question I got at the PhD defense was, okay, what happens if you have a shock, running around and interaction with expanding shock and some complicated? I don't know.
I know that
it may be tough. Yeah.
I think Grant Candler and Yanni Malcolm's done a paper sort of looking, it's somewhat related in the sense that they were doing the nozzle fill problem. Sometimes you've got these characteristics that focus in the center, and then sometimes the center looks bad, and why does the center of the nozzle look bad? And they found that if they made their grid follow the if they made their grid look like characteristics, all those problems.
Yes. So if you are close to this true characteristics, and then I think there you can use this minimization scheme to finish up this grid arrangement. The complicated cases, but there's some progress. If you know, the Aldo-Bombilio is from Italy. He's been working on shock fading. He has some results with shock, complicated shock and interactions with adapted, perfectly captured. Yeah, so there's progress.
So a triangular element being a linear element, even if it falls on something like active numbers, it doesn't completely say that it's planing along the surface because it's not plain on
Because the edges are mine, it doesn't fit the color.
It's the thing, like it's a how would I say it look like a 3D surface in X, Y, U, but then the triangle plane would never match on that surface. It at best be tangent to the surface. It won't fall on that. You have those things.
You're talking about the geometry.
Yeah, interpretation.
Like, what's the question?
You were saying, yeah, geometry. You were saying it's like you align it with the characteristics. When you have a simple equation, the characteristics is straight line.
Yeah.
But once you have a if it's a nonlinear system, then the characteristic is not a straight line. It's a surface in X and S or X. Then it's no longer you have to. There's no way you can align it.
It is not. Yeah, but for nonlinear system, you can show for those. That's a residual distribution scheme. You only look at the triangle. If the one edge is aligned with the characteristic, with the average characteristic scheme, like average diagonal. And then if the third node and the other two nodes satisfy granting you volume, it doesn't matter if this volume is 0 or no. The residual functions. And that's how you can generate this short aligned perfect solution. The problem is, difficult part is always this generation of discrete. Once you have something close, you can use this minimization scheme to make a little adjustment. So I have nonlinear results published in International Journal. And it has a perfectly short nonlinear shape.
But even if it's not perfectly aligned, so even if it's somewhere perfectly aligned and another place is not, it's still a better solution, maybe not perfect solution, but better solution.
Yeah, I think the interesting thing to me is that characteristic surfaces, certainly in context of the order equation, the equation and so on, makes sense. But when you actually compute a solution for those equations, it's interesting that you still get everything seems to work well. Now, if you did have a shock, for example, and that shock, say, is depending on the boundary layer and all these interactions, it's interesting that at least from what you're showing in these examples, it doesn't seem to make, maybe it doesn't make that kind of dramatic difference. That's an interesting aspect of this whole thing. Really comment on how this is thinking now.
There are so many strange phenomena.
Yeah, but I think there's lots of questions he still needs to answer. And maybe, but he's answered some important ones, but there are some really other important ones as well.
Have you tried to prove stability, linear stability?
No,
With a negative volume?
I didn't try, but
Or you should probably try for the time-dependent case with a negative volume.
At his point, it's going to be the same. It's basically his equation will look like regular time-dependent equation, just with sign minus.
yeah, and I did.
Sign
You know,
minus, you have the wrong.
No, both sides will have minus.
time derivative.
No, not only time derivative, both sides have minus.
Everything.
Time derivative multiplied by negative volume, and there is sign minus before summation of fluxes.
Yeah, everything has minus, so there's no problem. Is it? This is negative, and this integration is negative, gives you negative. So both negative. So this is the equation yourself. And for stability, yeah, I try to look at the accuracy and stability. And accuracy is, I think, easy because if you use Taylor expansion, Taylor expression doesn't care about zero negative volume elements. It just cares about how your neighbors are located. So the same proof goes through. And the energy stability of this first order HDA scheme was proved. And I need to look at this again, but I don't know if this proof cares about zero negative volume. Probably not.
Your volume being negative there, you no longer have a quadratic function.
Where
If the volume is negative, you're going to contract up against your entropy.
But it just
Everything-
like sign minus
everything
equals
has
the same
negative.
equation.
everything has negative sign. You can do manipulate this equation.
Multiply by -1, you get the regular time.
Yeah. Negative volume, dual volume, even dual negative volume, or negative. I don't see a problem because my code doesn't check based on my experience in PhD study. I don't have any check for negative volume. It just goes through, and so I published a lot of papers. Maybe some test cases I might have a negative volume, so I didn't care. But if the dual volume is negative, this requires some careful study, and I'm still working on this. But if everything is flipped, the grid is completely flipped, then there's you have negative volume everywhere, right? And you are solving negative of this. But therefore, depending on the scheme, you may need to modify it. Like a dissipation may have the same sign. It doesn't matter whether positive or not. And then you need to flip it. So most of the test cases I try to avoid negative dual volume. But I can have negative volume elements as long as the dual volume is possible. No problem.
Okay.
Here?
Thinking back to your PhD work
Okay.
and the driven cavity light bulb, and you showed that very crazy grid that resulted.
Yeah.
The solution looked good.
Yeah.
And I guess I'm just trying to figure out. I would have expected some kind of symmetry in the grid or something. It's just. But what kind of perturbation? I mean.
Okay, this was a Gauss-Seidel type of iteration. So the solution and points are adjusted here and then go to the next. So I didn't expect symmetry.
The ordering was not symmetric.
The ordering was not symmetric. So if you had started with, was your initial grid symmetric in any way?
Yeah, it's a regular mesh.
Regular mesh initially.
Yeah, and then points tries to move toward these two singularities. And in this case, the boundary points don't move.
I guess I don't understand why that would be an optimal solution. Just intuitively, why I would get something that looked so bad.
The here is I think minimum is not unique.
Yeah, that's the point.
Yeah,
So
depending on the
Multiple then.
yes, depending
so
on
this is just one of them.
just one local
Maybe 100 more.
Yeah.
Or maybe infinite number.
Okay.
I saw this grid. I'm one of those people who saw this but never told. So
Are you keeping him in the Twilight Zone?
I liked another one to be trailblazer.
Like this one, as long as you capture the show, this part, you can have any. The solution is constant. So certainly minimum is not unique. But
What happens if you have negative volume that's taking your solid surface?
solid.
You don't have control over that negative volume at any point. So they can connect you to your solid surface. Then you violate mass conservation complications come.
Mass
It
conservation.
will not get solution there. It will just still be interior points.
Yeah.
It just happened to be there, but it is interior point. It's not
As a
inside of the
laser,
surface.
if you are not checking for negative volumes, then you don't have control over that negative volumes.
It's interpretation of your solution.
Like,
If this is
Like here, the point is outside of the domain. So you may not have any physical solution outside of the domain, but your point is placed here. So you modify your domain.
No, but what nodal value would it be? What would be given to the
So it give you some like,
combination of this equivalent solution.
and it is not continuous there because it's a wall, solid wall.
you ignore your solid wall, so your domain changes. You do not honor the shape of your solid wall.
I mean, definitely this is a problem. This is a solid body. Yeah.
But it's an interpretation problem.
Yeah, but if you integrate, for example, pressure distribution over this boundary, then you get a pretty good prediction.
Pressure, I mean, pressure sometimes converges much together another quantity. You do this
Yeah, you can look for other quantities too. So. Okay, let's move to fun part. Thank you very much.